Okay, at the previous lecture we began to discuss C-star envelopes. So let's recall the definition. We start with a star algebra, A. So roughly the C-star envelope of A is a universal way of making A into a C-star algebra. More exactly, the C-star envelope of A is defined to be a pair consisting of a C-star algebra, C-star of A. So this is a C-star algebra, and a star homomorphism theta from A to C-star of A. And this pair is universal in the following sense. If we have another C-star algebra B and a star homomorphism phi from A to B, then there exists a unique star homomorphism psi from C-star of A to B such that this diagram commutes. So for every C-star algebra B and for every star homomorphism phi, there is a unique star homomorphism psi. In other words, this pair, from the viewpoint of category theory, this pair is an initial object in the category of all such pairs. And so we have a natural bijection between the set of all star homomorphisms from A to B and the set of all star homomorphisms from C star of A to B. And this correspondence is a natural isomorphism in the variable B. So here B runs over the class of all C-star algebras. Well, I don't claim that this object always exists. In fact, we will see shortly, by looking at some examples, we will see that sometimes C-star of A doesn't exist. But it exists if and only if, we proved that it exists if and only if, there is a largest C-star seminorm on A. So we define the following number. This is the supremum of P of A, where P runs over the class of all C-star seminorms on A. Or equivalently, we can consider all star representations of A and take the supremum over the norms of pi of A, where pi runs over all star representations of A. So this is something which looks like the largest C-star seminorm on A. And in fact, it is the largest C-star seminorm, provided that it is finite. And in fact, we proved that C-star of A exists if and only if this number is finite. This is finite for every A in A. And in this case, this is the largest C-star seminorm on A. And to construct the C-star envelope, we do the following. The C-star envelope of A is the completion of the quotient of A modulo the ideal I, consisting of those elements where our largest C-star seminorm vanishes. This is a two-sided star ideal, so we take the quotient and we equip this quotient with a canonical norm. So the norm of coset of A modulo I is just the seminorm of A. This is well defined and makes this quotient into a pre-C-star algebra. So this is a pre-C-star algebra. We take the completion and we get C-star of A. So we prove that this is indeed, the C-star algebra indeed has this universal property. In fact, we already proved, also proved that if we want to prove the existence of C-star of A, then there is no need to prove that this number is finite for all elements in A. In fact, we observed that it suffices to check this condition on a suitable subset of star generators of A. And in particular, we deduced that if, this is an important corollary, if A is generated by the entries of a family of unitary matrices over A of a family of unitary matrices over A, then the sister envelope exists. This is particularly useful in the theory of quantum groups, because many concrete examples of quantum groups or compact quantum groups are defined to be sister envelopes of suitable star algebras satisfying this condition. In practice, many concrete sister algebras are defined in terms of generators and relations. So let's introduce the respective terminology. Suppose we have a set, an arbitrary set I, and let F denote the free associative algebra, generated by free variables xi and yi, where I runs over our index set I. This is the free associative algebra. And suppose we have a family of elements in this algebra, as denoted by Pj, a family of non-commutative polynomials, a family of elements of F. And let K denote the two-sided star ideal. Oh, sorry, I forgot to define involution. Before speaking of star ideals, we must define an involution on F. The involution on F is uniquely determined by the following relation: xi star equals yi. It's a simple exercise to show that this rule uniquely extends. So we define the involution on the generators xi, but it uniquely extends to F. So F becomes a star algebra. Now we take a family of elements of our algebra, and let's denote by K the two-sided star ideal of F generated by this family, by the family Pj. And we define the universal sister algebra, or more exactly, the universal unital sister algebra with generators xi and relations Pj. Relations Pj to be the following sister algebra. It is denoted like this. And by definition, this is the sister envelope of the quotient of F modulo K. If it exists, of course. If it exists. So if we now look at the definition of a sister envelope, we conclude that this universal sister algebra has the following universal property. Universal property of this algebra. For every unital sister algebra A, and for every family of elements AI of elements of A, such that these non-commutative polynomials vanish at AI and AI star, Pj applied to AI, AI star vanishes for all I and j. There is a unique unital star homomorphism psi from this universal C-star algebra to A, such that psi of xi, so it takes the generators xi to the elements AI for all I. Well, why is this so? This is indeed true because if we have these relations, it follows that first we use the universal property of the free algebra. It is free, so we can, of course, we can always construct a homomorphism from F to A, which takes xi to AI and yi to AI star. And this will be a star homomorphism because of this relation. And now, this property implies that this homomorphism from F to A factorizes through the quotient of F modulo k to A. And now, since A is a C-star algebra, we simply use the definition of the C-star envelope and extend this to the C-star envelope. And this is our homomorphism psi. So basically, this universal property follows from the definition of the C-star envelope and from the universal property of the free algebra. Sometimes we will also consider the commutative version of this construction. So we define the, well, let me write this down explicitly. We define the universal commutative C-star algebra with generators xi and relations pj to be the universal C-star algebra with the same generators, the same relations, and also with the commutation relations between the generators. So xi x k minus x k xi and xi xk star minus xk star xi. So we add the commutation relations between the generators. So as a result, this algebra is commutative. And moreover, it's easy to observe that it has a similar universal property, but only the class of commutative C-star algebras. So this is the universal commutative C-star algebra with generators xi and relations pj. Okay, so let's now look at some concrete examples of C-star envelopes. Examples of C-star envelopes. Example 1, let A be the Laurent polynomial algebra in variable t, the Laurent polynomial algebra in variable t. We make it into a star algebra as follows. We define the involution in such a way that t is unitary. T star equals t inverse. So what can we say about the C-star envelope of A? So first of all, we observe that this is just, if we use this terminology, then this sister envelope is the universal sister algebra generated by a unitary element, by a single unitary element. And it's a simple exercise to show that this algebra is isomorphic to the algebra of continuous functions on the circle. So bold T is the unit circle on the complex plane. A hint to the exercise is to use the functional calculus. Да, это просто практически по определению. This follows from the universal property of the Laurent polynomials. And this is an exercise. More generally, we can consider the algebra of Laurent polynomials in several variables, say T1, Tn. The Laurent polynomial algebra in several variables. Again, we define an involution in such a way that each generator is unitary. Ti star equals Ti inverse. And in this case, the sister envelope of A can be identified with the universal commutative sister algebra generated by n unitaries, U1 to Un. And this universal algebra is isomorphic to the algebra of continuous functions on the n-dimensional torus. So this is a natural generalization of example 1. Example 3. Let's now take the polynomial algebra, or we can equally well take the Laurent polynomial algebra. This doesn't matter in this case. And we define an involution in such a way that the generator T is self-adjoint. Not unitary, but self-adjoint. What can we say about the sister envelope in this case? Well, it would be natural to call this algebra the universal unital sister algebra generated by a self-adjoint element. But in fact, this algebra doesn't exist. So this is the simplest example of the situation where the sister envelope doesn't exist. Example 4. This is the so-called Weil algebra, the Weil algebra. The Weil algebra is defined to be the algebra generated by two elements, P and Q, and the following commutation relations. Commutation relation, actually only one relation. The commutator of P and Q is I times the identity. This is the standard algebra of quantum mechanics. In quantum mechanics, the generators P and Q are interpreted as the basic observables. Q is the coordinate, and P is the momentum. And the commutator is given by this formula. This corresponds to the Heisenberg principle. The involution is naturally defined such that P and Q are self-adjoint, which is also quite natural from the point of view of quantum mechanics. Well, observables are always self-adjoint. What can we say about the sister envelope of this algebra? Well, the sister envelope does exist, but it is zero, which means that to deal with quantum mechanics, we cannot use bounded linear operators. We must use unbounded operators. Example 5. Example 5 is the so-called choplets algebra. The choplets algebra. The choplets algebra, that's denoted by T, script T, is defined to be the universal unital C-star algebra generated by an isometry. So what is an isometry? In an abstract star algebra, unital star algebra, an element U is called an isometry if it satisfies this condition. Universal unital C-star algebra generated by an isometry. This terminology is quite natural because it's a simple exercise in functional analysis to show that an operator U on a bounded operator U on a Hilbert space is an isometry in the usual sense. That is, it preserves the norm if and only if it satisfies this condition. It turns out this is an exercise, and this exercise is not entirely trivial. In the next exercise sheet, I'll give some hints to this exercise. This algebra turns out to be isomorphic to the algebra, to the C-star subalgebra of B of L2, C-star subalgebra of B of L2, of the algebra of bounded operators on the Hilbert space little L2, generated by the shift operator. The shift operator. Sorry, I forgot. So some time ago, maybe indeed we have already defined this algebra. In fact, these two definitions are equivalent. So we can define it either as this subalgebra or as the universal algebra generated by an isometry, but these definitions are equivalent. This exercise is known as Coburn's theorem. Another useful example. Example 6 is the so-called the two-dimensional quantum torus. The quantum two-dimensional torus. Or the rotation algebra. So we take a real number, theta, and we define a theta to be the universal C-star algebra generated by two unitaries. U and V are unitary, satisfying the following commutation relation. UV equals the following number, the following exponent, VU. So this is the commutation relation between U and V. It exists because U and V are unitary. So universal C-star algebra generated by a family of unitaries is always defined, and it exists. If in the special case where theta is 0, we come back to this example. If theta is 0, then they commute. So let's observe that if theta is 0, then if theta is isomorphic to the algebra of continuous functions on the two-dimensional torus. This is example 2. In the general case, if theta is not 0, then this algebra is non-commutative. So a useful exercise, which is not entirely trivial, but again, I'll give you a hint in the exercise sheet, is that this algebra can be defined more explicitly under the assumption that theta is irrational. So suppose that the number theta is irrational. Then theta is isomorphic to the C-star subalgebra of the algebra of bounded operators on the L2 space on the circle, generated by the following two operators, big U and big V, where the operators U and V are given as follows. U is just the multiplication by the coordinate, so it takes f of z to z f of z. And V is the rotation operator given by the following formula. So in some sense it rotates the circle by the angle theta, by the angle 2 pi theta. If it is irrational, then this is not true. For example, if theta is 0, then this is just the identity operator. And U and V generate the algebra isomorphic to C of t. Not this one, but the algebra of continuous function on the circle. So if theta is 0, then this is not true. And in fact, it is not true if theta is rational. It is not very easy to show this, but this is true. If theta is rational, then this algebra, this subalgebra is a quotient of theta, but they are not the same. But if theta is irrational, then these algebras are isomorphic. Example 7 is quite short. If we take two C-star algebras A and B, two C-star algebras, then the C-star envelope of their algebraic tensor product is nothing but the maximal C-star tensor product of A and B. And this is true almost by definition. If we recall the maximal, the explicit formula for the maximal C-star norm on the algebraic tensor product, we see that this is exactly the maximal norm on the algebraic tensor product. So these algebras are the same. Example 8. Let G be a group. So we may consider it as a topological group with a discrete topology. So just a group. And let A be the group algebra of G. The group algebra over the complex numbers. Let's define an involution in such a way that every element of G is unitary. So this rule easily extends to an involution. So this determines an involution on the group algebra. So it becomes a star algebra. The C-star envelope exists, again, because the generators are unitary. And the C-star envelope is called the full group C-star algebra of G. And it is denoted by C-star of G. So this is the full group C-star algebra of G. What can we say about this algebra? So it exists. Is it big? To answer this question, let's recall that some time ago we defined the so-called reduced group C-star algebra of G, which is generated by the regular representation of our group, and that the group algebra of G is embedded as a dense subalgebra into the reduced group C-star algebra. So we can look at the following picture. This is the group algebra. This is the reduced group C-star algebra. So we have an inclusion here. On the other hand, the universal property of the C-star envelope gives us a star homomorphism from the full group C-star algebra to the reduced group C-star algebra, such that this diagram commutes. So in particular, we see that this map is also an inclusion. It is injective. And this is a surjective star homomorphism. Why is it surjective? It is surjective because it has dense range. So the group algebra is contained in the range of this homomorphism, but on the other hand, we know that the range of star homomorphism between C-star algebras is always closed. So it is surjective. And so the reduced group C-star algebra becomes a quotient of the full group C-star algebra. A natural question is it an isomorphism? And the answer depends on the group G. So the fact, which is rather non-trivial, says that this map is an isomorphism even only if the group G is amenable. Well, I'll not give a formal definition of an amenable group because it is not directly related to our course, but this is a very classical notion which goes back to von Neumann. One of the equivalent definitions is that G is amenable if there is functional on L infinity of G, on the space of all bounded functions of G, which is non-trivial, that is non-zero, and the left invariant. It is invariant under translations. Moreover, we can assume that this function is positive and normalized, and in this case, it is called the invariant mean on G. But in fact, there are many other equivalent definitions of amenable groups, and this is a very important notion in analysis and in many applications to various subjects of mathematics. Okay, probably that's all I wanted to tell you about C-star envelopes. Some other examples of C-star envelopes will appear in the context of quantum groups. So now let's begin. Let's turn to compact quantum groups. Quantum groups are very popular objects in modern mathematics, but at the same time, there is no formal definition of a quantum group which applies to all possible cases. On the other hand, we will see shortly that there is a formal definition of a compact quantum group. But let's start with some motivation. We already know the Gelfand-Namelach duality, which states that the category of compact Hausdorff topological spaces is dual or anti-equivalent to the category of commutative unital C-star algebras. And a similar result exists in algebraic geometry. So a category theoretic form of Hilbert's Neustadt Satz says that the category of affine algebraic varieties over the complex numbers is anti-equivalent to the category of commutative unital algebras, commutative unital finitely generated algebras without nilpotence. So according to the general philosophy of non-commutative geometry, non-commutative algebras can be interpreted, and sometimes should be interpreted, as algebras of functions on non-commutative spaces or on quantum spaces, on spaces which don't exist. And different types of algebras correspond to different types of spaces. For example, unital C-star algebras may be interpreted as algebras of continuous functions on compact Hausdorff topological spaces. But now, what are algebras of functions on quantum groups? Well, a group is a space, maybe a topological space or an affine variety or just a set equipped with an extra structure, that is a multiplication. And well, since we want to interpret quantum spaces or algebras of functions on quantum spaces as arbitrary non-commutative algebras, then algebras of functions on quantum groups must be algebras equipped with an extra structure which somehow corresponds to the multiplication on a group. And to identify this extra structure, let's first look at the definition of a group, and let's try to dualize this definition, that is translated into language of algebras. So suppose, for convenience, we will start not with the case of groups, but rather with the case of semigroups. So suppose that G is a semigroup, and let f of G be an algebra of functions on G. Well, it's natural to take the algebra of functions which somehow is compatible with an extra structure G. Actually, we will be interested in the following two cases. Case one is the case where G is a fine algebraic semigroup. For example, we can take the full linear group GL and C of invertible matrices, or the special linear group of unimodular matrices with determinant 1. Or we can also take the semigroup, the multiplicative semigroup of all matrices. It is not a group, but it is a semigroup. In this case, we take for f of G the algebra script O of G of regular functions. Regular or polynomial functions on G. So if G consists of all matrices, then this is the algebra of all polynomial functions. In the general case, if G is one of these two groups, then we just restrict the polynomials on the semigroup of matrices to G. In this case, let's recall then that, well, this is a standard fact in linear algebra that there is an algebra isomorphism between the tensor product of O of G by itself and the algebra of regular functions on the product of G by itself, G cross G. And the isomorphism is quite explicit. It takes every elementary tensor in this tensor product to the function given by the following formula. H of xy equals f of x times g of y. This is an algebra isomorphism. The second case we're interested in, and actually this is our main case, is the case where G is a compact topological semigroup. So case 2 is the case where G is a compact topological semigroup. And in this case, we consider the algebra of continuous functions on G. So f of G is just C of G. And let's recall that we have a star isomorphism between the minimal spatial C star tensor product of C of G by itself and the algebra of continuous functions on the product of G by itself, given by the same formula. So it will be convenient to consider both cases simultaneously. So let A be the algebra of regular functions of G in case 1. And let A denote the algebra of continuous functions in case 2. And also in case 1, we take the usual algebraic tensor product. In case 1, this symbol, as usually, denotes the algebraic tensor product. And in case 2, it's natural to take the spatial C-star tensor product. Okay, so G is a semigroup by assumption. So it is equipped with the multiplication map G cross G to G. That's denoted by M. And this map is associative. So we have the following commutative diagram, which represents the associativity of this map. This is M, this is M, this is M cross 1. 1 is the identity map, and this is 1 cross M. And the diagram is commutative. Okay, now let's dualize this map. So our algebra is the algebra of regular functions in case 1, or the algebra of continuous functions in case 2. But in both cases, this map can be dualized, and it gives us an algebra homomorphism from A to A tensor A. We denote it by delta. And delta is given by the following formula. Delta of f sits in this tensor product. This tensor product is just the algebra of functions of two variables, both in case 1 and in case 2. So we make these two identifications. So delta of f is a function of two variables, and it is given by the following formula. It is simply f of xy. So delta, in some sense, dualizes the multiplication on M. Now, the associativity of the multiplication in our semigroup leads to the following commutative diagram. A tensor A. This is delta. Here we have A tensor A. Now this is delta tensor 1, and this is 1 tensor delta. And this diagram is commutative because this one is commutative. So this observation naturally leads to the definition of a bi-algebra. First of all, we give the following definition. By definition, a co-algebra is a pair, A delta, where A is a vector space, and delta is a linear map from A to A tensor A, a linear map, such that this diagram commutes. That's denoted by, for example, star. Such that the diagram star commutes. The map delta is called the co-multiplication. On A. And the commutativity of the diagram says that this co-multiplication is co-associative. The diagram star means that delta is co-associative. In our concrete example, A was not just a vector space, but was an algebra. So we say that a bi-algebra is an algebra A together with a co-multiplication such that, first of all, A together with delta is a co-algebra. A delta is a co-algebra. And delta is an algebra homomorphism. Delta is an algebra homomorphism. Usually, when we speak about bi-algebras, we mean unital bi-algebras. So let's make this assumption more precise. A unital bi-algebra is a unital algebra such that all these conditions are satisfied. Delta is also unital. And finally, if, moreover, A is a unital C-star algebra, the tensor product sign means the minimal C-star tensor product, and delta is a star homomorphism. Then we say that A together with delta is a unital C-star bi-algebra. A unital C-star bi-algebra. We will not consider the non-unital case. Now, I'll only say that in the non-unital case, the definition is not so straightforward, because in the non-unital case, delta acts not to the tensor product of A by itself, but to the so-called multiplier algebra, which is strictly bigger than the tensor product. But this notion is not related to compact quantum groups, so we'll consider only unital C-star bi-algebras. And actually, we already have a typical example. Example 1. If G is an affine algebraic semigroup, then O of G, the algebra of regular functions, is a unital bi-algebra. And similarly, if G is a compact topological semigroup, if G is a compact topological semigroup, then C of G, the algebra of continuous functions on G, is a unital C-star bi-algebra. Unital C-star bi-algebra. And it is commutative. C of G is commutative, of course. Now we have the following simple result, which says that actually this example, example 2, describes all commutative unital C-star bi-algebras. Theorem 1. Suppose that A is a commutative unital C-star bi-algebra. And let G denote the maximal spectrum of A. So the co-multiplication can be dualized, so we can consider the map from the maximal spectrum of A tensor A to the maximal spectrum of A. So this is delta star. But the maximal spectrum of A is G. And the maximal spectrum of the tensor product is actually isomorphic, more exactly homeomorphic, to G cross G. Because we know that because A is commutative and unital, it is isomorphic to C of G, to the algebra of continuous functions on the spectrum. And the tensor product of two copies of the algebra of continuous functions is isomorphic to the algebra of continuous functions on the direct product. So the maximal spectrum of this is just G cross G. So as a result, we get a map, a continuous map from G cross G to G. And I claim that G together with M is a compact topological semigroup. And moreover, the Griffon transform from A to C of G is an isomorphism of unital C star by algebras. Of unital C star by algebras. Well, to make this statement precise, I must also explain what is a morphism of C star by algebras. But this is rather straightforward, so let's give the respective definition. You have two unital C star by algebras A and B. And a star morphism phi from A to B. When we say that phi is by algebra homomorphism, if the following diagram commutes, so this is phi from A to B, here we have the co-multiplication on A, the co-multiplication on B, and here we have a phi tensor phi. So we say that phi is a bialgebra homomorphism if the diagram commutes. This is a rather natural definition of a bialgebra homomorphism. The proof of theorem is rather straightforward, modulo the Griffon-Nymark duality. Proof of theorem 1. Namely, if we look at this diagram, which represents the co-associativity of delta, and dualize it, we conclude that M is associative. So delta is co-associative. And if we combine this with the Griffon-Nymark theorem, we deduce that M is associative. So G is a semigroup. We know that gamma is an isomorphism of C star algebras, and it's a straightforward exercise to show that the diagram commutes. So gamma is actually a bialgebra homomorphism. This is a straightforward exercise. So as a result, we see that all commutative unital C star bialgebras are algebras of continuous functions on compact topological semigroups. This result can be complemented by the following simple exercise, which tells us something about morphisms between such objects. Namely, if we have two compact topological semigroups, say G and H, G and H are compact topological semigroups, and phi is a continuous map from G to H, then of course phi induces an algebra homomorphism, phi dot from C of H to C of G, which acts as the composition with phi. So it takes F to F composed with phi. This is an algebra, a star homomorphism. And the exercise is to show that phi is a semigroup homomorphism. If and only if phi dot is by algebra, a C-star by algebra homomorphism. So if we now combine this exercise with theorem 1, we see that we get the following corollary. There is an equivalence of the following two categories. The category of compact topological semigroups, or more exactly the dual of this category, the opposite category, is equivalent to the category of commutative unital C-star by algebras. And the equivalence is just the Gelfand-Nymark duality. So this arrow is the functor C, and this is the functor max, which we already know about from the Gelfand-Nymark theorem. Okay, this is very nice, but this is not exactly what we need. So we are mostly interested in groups rather than in semigroups. So our next goal will be as follows. We want to construct a full subcategory. We'll denote it as CQG. So the objects of this category will be called the compact quantum groups. It will be a full subcategory in the category of all unital C-star by algebras. In such a way that the commutative part of this subcategory, category of commutative compact quantum groups, is antiequivalent to the category of compact topological groups by the Gelfand-Nymark duality. So this is what we want to do. Well, how can we define such a category? A possible approach to constructing such a category is based on the notion of a Hopf algebra. A possible approach is based on using Hopf algebras. Well, maybe some of you are already familiar with the notion of a Hopf algebra. I'll not give you a formal definition now. So roughly a Hopf algebra is a bi-algebra, A delta, equipped with an extra structure, that is with two maps, epsilon and S, where epsilon is an algebra homomorphism from A to the complex numbers, and it is called the co-unit of A. And S is a linear map from A to itself, and it is called the antipode from A. So all these maps must be somehow compatible to each other and compatible with the co-multiplication. I'll not write the compatibility axioms now, but I'll give a basic example. If G is an affine algebraic group, then O of G, the algebra of regular functions, is a Hopf algebra in a natural way. So the co-unit is just the evaluation as the identity, and the antipode is responsible for the inversion map on the group. So as f of x is f of x inverse. In fact, we can define the notion of a Hopf-Sistar algebra in a similar way. Indeed, if we take the algebra of continuous functions on a compact topological group, then we may define a co-unit on C of G and the antipode by exactly the same formulas. And this naturally leads to the notion of a Hopf-Sistar or to the notion of a Hopf-Sistar algebra. So, and in fact, this approach works. So if we define this subcategory to be the category of Hopf-Sistar algebras, of unital Hopf-Sistar algebras, then actually we get what we need here. But it turns out that this approach is too naive. If we define compact quantum groups to be Hopf-Sistar algebras, then we must throw away many natural examples of compact quantum groups, including, for example, the basic example of the quantum SU2 defined by Voronovich. We will see shortly, well, not shortly, but maybe at the next lecture, that there are many natural examples of compact quantum groups which don't have an antipode and sometimes even don't have a co-unit. So as a result, this approach works formally, so it satisfies this condition, but it leads to a very narrow class of compact quantum groups. So this approach leads to a very narrow class. Of objects. So we must use a different approach. So our strategy will be as follows. First, we try to define a compact topological group in a slightly non-traditional way. That is, by avoiding the existence of an identity and by avoiding the existence of the inversion map. Then we dualize the resulting definition of a compact topological group, write it in dual terms, in terms of function algebras, and as a result, we arrive to the definition of a compact quantum group. So this is our plan. Let's now give some definitions. Suppose that G is a semigroup and I is a non-empty subset of G. We say that I is an ideal of G if it is stable under multiplication by elements of G. That is, if xi is contained in I and ix is contained in I for every element in G. By the way, it's easy to observe that if G is a group, then the only ideal is G itself. Observe that if G is a group, then I necessarily equals G, because it is non-empty. If we take an arbitrary element in I and multiply by the inverse, we conclude that the identity sits in I, and an ideal containing an identity is necessarily equal to G itself. So non-trivial ideals can exist only in the case where G is a semigroup but is not a group. And we need another definition. we say that G is a semigroup with cancellation. If it satisfies the following condition, if every equality of the following form can be simplified by canceling I on the right. x1i equals x2i implies that x1 equals x2. And similarly on the right, on the left, sorry. On the left, if y x1 equals y x2, then this implies that x1 equals x2. A typical example is, of course, the set of natural numbers, which is an additive semigroup with cancellation. Well, of course, every group is a semigroup with cancellation. It's clear because we can also always multiply by the inverse element, y inverse. It turns out that the cancellation property characterizes compact topological groups within the class of compact topological semigroups. So we have the following result. This is theorem 2. If G is a compact topological semigroup with cancellation, then G is in fact a topological group. A topological group. Well, to prove this result, we take an arbitrary element, little x, in G, and let H denote the closed sub-semigroup, the closed sub-semigroup of G generated by X. Generated by X. So it is a commutative sub-semigroup of G. Basically, this is the closure of elements of the form x to the power n. And let's also introduce the following set. Let I denote the intersection of all closed ideals of H. The intersection of all closed ideals of H. Now, a standard compactness argument implies that I is non-empty. This is a useful exercise in general topology. Basically, we have to check that I satisfies, this family satisfies a finite intersection property. That is, the intersection of finitely many closed ideals is a closed ideal, is non-empty, And so now the standard compactness argument implies that the intersection of all such ideals is also non-empty. Well, clearly, it is also a closed ideal. So we conclude that I is the smallest closed ideal of H. Let's now observe that for every element y in H, we have the following equality: yi equals I. Well, indeed, yi, this product, is also easily seen to be a closed ideal of H. And it is contained in I, because I is an ideal. But I is the smallest closed ideal, so they should be the same. Okay. In particular, let's now take an element y in I itself. Let's take any element y belonging to I. Then this equality implies that there exists an element E in I such that ye equals y. Now let's apply the cancellation property. We take an arbitrary element z in G, we multiply this equality by z on the right and cancel I on the left. And we see that Ez equals z. So E is a left identity in G. And let's now apply the cancellation property once again. We take an arbitrary element W in G. We multiply this equality by W on the left and cancel Z on the right. And we deduce that WE equals W. And if we now compare these two equalities, we deduce that E is an identity. E is an identity of G. Okay, so G has an identity. Now we have to show that every element is invertible. So we have already taken an arbitrary element X. Let's show that X is invertible. X belongs to H, of course. And so we may apply this equality to X. So this implies that Xi equals I. And in particular, we see that there is an element Y in I such that Xy equals E. Now we use the cancellation property once again. We multiply it by Y. We multiply this equality by Y on the left. And then we cancel Y on the right. And we deduce that Yx equals E. And we compare this and this. And we conclude that X is invertible. So G is a group. G is a group. Formally, we have to check also that the inversion map is continuous. So by definition, a topological group is a topological space together with the structure of a group such that the multiplication and the inversion map are continuous. So why is the inversion map continuous? Here we use the compactness argument. We look at the following map from G cross G to itself, which takes xy to xy. And this map is a continuous bijection. It is a continuous bijection, and G cross G is a compact Hausdorff topological space. Well, when we speak of compact topological semigroups, we always assume that it is Hausdorff. Sorry, I forgot to tell you about this, but this is a standard convention. So a compact semigroup is a compact Hausdorff semigroup. So it is a compact Hausdorff topological space, and this is a continuous bijection. And this implies that the inverse map, which is given by the following explicit formula, it takes xy to x inverse y. So this map is continuous. And the continuity of this map easily implies that the map which takes x to x inverse is also continuous. We simply substitute the identity for y, and we deduce that this map is continuous. And that's it. So this shows that G is a topological group. So every compact topological semigroup with cancellation is a compact topological group. Let's now try to dualize the cancellation property. That is, to write it in terms of the algebra of continuous functions. And as a result, you get the following theorem, theorem 3. Suppose that G is a compact topological semigroup. Let A be the algebra of continuous functions on G. And let delta be the standard co-multiplication on A. given by the following formula. Then the following conditions are equivalent. Condition 1, G is a topological group. And condition 2, the following two subspaces, delta of A multiplied by 1 tensor A, and delta of A multiplied by A tensor 1, they are dense in the tensor product of A by itself. Okay, so, well, probably it's time to finish now. So let me only say why is it useful. It is useful for the following reason. Basically, this was the main motivation for Voronovich when he defined compact quantum groups. So we define following Voronovich, we define a compact quantum group to be a unital C-star by algebra satisfying condition 2. On the one hand, this definition is reasonable because in the commutative case, this definition is dual to the definition of topological group. So we will see that commutative compact quantum groups are just algebras of continuous functions on compact topological groups. And on the other hand, this density condition is quite flexible. And we will see that there are many natural examples of compact quantum groups, that is, of unital C-star by algebra satisfying these conditions, which cannot be determined in terms of Hopf algebras. Okay, so that's all for today. So at the next lecture, we prove this result and discuss some concrete examples of compact quantum groups.